So, we will continue our discussion on flow in a converging nozzle. So, flow in a converging nozzle. And what we have stated that let us have a converging nozzle which is connected to a reservoir where flow velocity is 0 and pressure and temperature are of course, the total pressure and total temperature, and at the other end we can control this pressure by some valve mechanism where the pressure is P b controlled by appropriate mechanism say as an example valve. And then the flow is going out through the exhaust. The pressure at the exit plane will denote as P e, that is pressure on the exit plane. And then we have discussed how this flow will develop as P b is decreased gradually. We have seen that there is distance along duct, So, this is the end of the duct exit plane. When P b equal to P 0, P b equal to P e equal to P 0, definitely there will be no flow, because in inviscid flow the pressure gradient is the only driving mechanism, and since there is no pressure gradient there will be no flow. Now, if the pressure is gradually decreased, there will be a flow and pressure will continuously fall to the value of P b at the exit plane. If it is still reduced, the flow velocity will increase, mass flow rate will increase, and these are all P b equal to P e, but that is less than P 0. If we continue to decrease this P b, then we will reach to a condition of P e equal to P b equal to P star, which we have derived earlier in our one dimensional flow analysis, at which the flow velocity in the exit plane reaches sonic value. So, corresponding to P b by P 0 equal to P star by P 0, which we know that equal to 0.528 for perfect gas with gamma equal to 1.4. When gamma equal to 1.4, if this P b by P 0 value is brought down to 0.528, then the flow velocity at the exit plane will reach sonic, and that is the maximum speed that can be achieved in a converging duct. Further reduction in the pressure, that is further reduction in the back pressure, will not affect the flow in the nozzle, that is within the flow this will this part, this pressure distribution will prevail. Let us call this belongs to flow regime 1, where we have seen that back pressure must be equal to exit pressure, or if exit pressure cannot be different from the back pressure as long as this flow is subsonic, and once the flow speed at the exit plane becomes sonic, the pressure at the exit plane become P star, and a further reduction in back pressure is not going to affect the flow within the nozzle. That is, the further expansion from P star to P b will take place outside the nozzle. In regime 2, in flow regime 2, which you can show here, a pressure below this that is P b by P 0 less than P star by P 0. No change within the nozzle. Exit plane pressure P e remain fixed at P star, and further expansion outside the nozzle and this cannot be analyzed using 1D analysis. Using one dimensional analysis, this part of the flow we cannot analyze. So, in the nozzle flow we can make in two regimes. In regime 1, we have P b by P 0 greater than P star by P 0, P e P b, exit Mach number less than 1.0, and as you decrease the pressure from P 0 to P star, the mass flow rate continuously increases. That is, that mass flow rate m naught T 0 by A e P 0 depends on P b by P 0. Eventually, this mass flow rate increases with decrease in P b by P 0. In regime 2, I have already stated that P b by P 0 is less than P star by P 0, P e equal to P star M e and m dot root T 0, that is the mass flow rate, is constant. So, what you see that the regime 2 is basically choked flow region. Regime 2 is choked flow region. Now, we can show how this mass flow rate variation of mass flow rate with back pressure when P b by P 0 is 1, there is no flow. So, mass flow rate is 0. This is the value for P star by P 0, and so this part belongs to regime 2, this part belongs to regime 1. In regime 1, as the pressure ratio decreases, P b by P 0 decreases, the mass flow increases. So, these are corresponding to those different curves that we have shown there. So, this is what we call regime 2, the choked flow region, and this is the unchoked region. We can also see that a relationship between the exit pressure and the back pressure. Let us say this is correspond to P star by P 0. When P b by P 0 is say 1.1, in regime 1 the back pressure and exit plane pressure they are same. So, these are however, once the back pressure reaches that P star value of P star, then further reduction in back pressure is not going to affect the exit plane pressure, and the exit plane pressure remain constant in this regime 2, the choked flow regime and the unchoked flow regime. Now, given a duct and the initial conditions and from the specified value of back pressure, we can calculate all the flow quantities using those isentropic area pressure relation, area Mach number relation and other isentropic flow relation. Now, let us discuss called the converging diverging nozzle. Converging diverging nozzles, also quite often called CD nozzles. They are also known as Laval nozzle. Once again, let us consider that this converging diverging nozzle is connected to a reservoir. A reservoir where the flow velocity there is no flow and P 0 T 0 they are held constant, and this P 0 T 0 are held constant. This is the exit plane, and let us say this is in the downstream again connected to a mechanism through which we can control back pressure, which can be controlled this is the throat. Now, Once again, considering this controlled pressure, let us say how the flow will behave within the nozzle as the back pressure is controlled. So, this is once again distance along duct. This is the exit plane. When P by P 0 is same as P b by P 0, there is no flow. Now, if back pressure is decreased gradually, let us say that this is the location for the throat. Throat plane. If back pressure is slightly decreased, a flow develops, and within the converging part of the duct, the flow accelerates to a certain speed, and then in the diverging part that flow will decelerate, and again pressure will increase and will reach to this value of P b. Still little decrease, flow velocity will increase, mass flow rate will increase, and now at the throat plane this is the value of the pressure that will be reached, and again the flow will decelerate. In all these situations, the flow everywhere remains subsonic, and exit pressure will become same as the back pressure. Let us say now what we see here, that the pressure at the throat is smaller than the pressure at the exit plane or back pressure. So, for a certain value of back pressure, let us say for a certain value of back pressure, the pressure at the throat plane reaches the critical value. Let us say this is the critical value P star by So, for this particular value of the pressure, let us say that we have reached what is the sonic pressure at the throat, and flow velocity at the throat also becomes sonic. However, the pressure at the back is not yet sufficiently low to cause further expansion in the diverging part. Consequently, the pressure in the flow in the diverging duct will again decelerate and will reach to this value P b. However, if the pressure value is back pressure corresponds to say this level, then we will see that there will be an fully expansion to the nozzle exit plane. We will denote all these curves by say 1, this by 2. Now, what happens if the back pressure is something between this and this? Then the flow in the diverging part is not fully isentropic. For any intermediate value of pressure, say here, the flow initially will accelerate or expand in the diverging duct, reach to a certain supersonic speed, and then will have a normal shock, and then it will further diffuse to the back pressure. Call both these curves at 3. At certain back pressure, we will denote it 4, where the shock will stand at the exit plane and anything in between the normal shocks, and any pressure between this point and between this level and this level, then there will be no more normal shock at the exit plane. However, oblique shock will develop from the lip of the nozzle, and they will interact in the jet downstream, and through repeated interaction of between the oblique shock and expansion waves in the jet downstream, the ultimate pressure will be established. So, that this will be something like this we call 5, and this level we will call 6, and any pressure level below this full isentropic expansion level, that is denoted here by 6, we will have expansion fan originating from the lip at the exit plane of the nozzle, and those expansion fan will interact, and then series of such expansion fan and oblique shock interaction, the final pressure or final expansion will be completed in the jet. Now, we will denote these as flow regime 1, flow regime 3, this will be flow regime 4. So, in regime 1, flow is subsonic, the converging duct, converging diverging duct, the converging diverging duct behaves like a venturi. Behaves as a conventional venturi. That P E equal to P B and flow rate depends on P B, which we are denoting by this curve or any curve within this region. At condition 2, we have seen that here the flow reaches the sonic value at the throat. However, the back pressure not being sufficiently low, further expansion is not possible. So, there is a very weak, in a sense very weak, almost 0 strength shock wave or Mach wave at the throat, and then pressure decreases gradually to the level of back pressure. Now, between this level 2 and 4, which we are saying regime 2, the flow downstream of the throat accelerates to some supersonic flow and then decelerates to a subsonic flow through a normal shock, and further downstream pressure gradually increases to reach the back pressure at the exit plane. Now, the location of the shock will of course depend on the value of the back pressure. As you can see that as the back pressure decreases, the shock moves downstream. So, a normal shock in the diverging portion part, shock moves downstream as P B by P 0 decrease. So, here also the exit plane pressure is virtually identical to this back pressure. However, in this case mass flow rate is there is any pressure below the level of pressure at 2, the flow in the converging part remain unaffected and the flow is choked, that is there is no further change in mass flow rate. Since shock moves downstream as P B by P 0 decreases as P b by P 0 decreases. So, when the pressure back pressure reaches the level of 4 in the earlier figure, then the shock moves furthest that is at level 4 in the figure, at level 4 in the figure, shock stands at the exit plane and at any pressure below that of level 4, there will be no more normal shock anywhere in the nozzle. Now, what you see that if we can increase the exit plane, that is at the exit, if we fit a duct of uniform cross section, then that entire duct or at the uniform duct now behaves like the exit plane and the real exit is at the exit of the uniform duct. And what happens then, that a supersonic Mach number exists everywhere in that uniform duct or constant area duct, and the flow becomes subsonic at the end of the constant area duct. And this constant area duct then can be used as a supersonic wind tunnel. So, you see that the pressure level, back pressure level 4 is the maximum back pressure at which we can have a supersonic wind tunnel operate. Now, see that in the regime 3, where we have back pressure which is higher than the pressure level 6, which is the pressure value for fully isentropic expansion in the converging diverging duct. We have no normal shock anywhere in the duct, but oblique shock appears at the lips of the nozzle at the exit plane. And what we see that the back pressure is higher than the pressure at the exit plane. So, we say that the nozzle is now over expanded, that is the expansion that we have allowed, the value of P b that we have set, the value at the pressure at the exit plane is smaller than that. So, in the nozzle the flow has undergone an over expansion, and consequently, this over expansion will be adjusted by subsequent compression in the jet downstream. So, in regime 3, these are over expanded nozzle, adjustment to P b occurs in the jet that is outside the nozzle. And this compression is achieved by oblique shock from the lip of the nozzle at the exit plane and downstream interactions. Because what in essence happens is that at the from the lip the oblique shock generates and they reflect from the jet boundaries, which in essence is a constant pressure boundary, but not a solid boundary, and from these reflections and their interactions a complex flow pattern develops in the jet, and finally, the pressure reaches the value of back pressure far downstream. The pressure level 6 is basically the downstream or the design condition for supersonic nozzle, where the exit pressure is identical with the back pressure. So, condition 6 P b having the design value for supersonic nozzle and in this case P e equal to P b and there is the flow everywhere in the nozzle and also in the jet outside is isentropic. Flow within the nozzle and downstream jet is isentropic. There are no shock, neither normal nor oblique, nor any expansion wave, nor any expansion fan. The perfect isentropic expansion in the duct. Now, in regime 4, P b less than design value of level 6, in this case P e is greater than P b, that is further expansion is possible. So, the flow has not been able to expand to its the full capacity. Flow has not expanded to the set value in the nozzle. So, this implies further expansion downstream. In the downstream jet. And we call this nozzle to be under expanded. This further expansion starts through expansion fan from the lip, and once again these expansion fan they reflect and interact and finally, the pressure is adjusted to the back pressure far downstream from the exit plane. Now, once again looking back to the pressure distance curve, we can see that there are infinite number of isentropic solution possible for the subsonic part, or that is within the regime 1. However, there is only one fully isentropic solution for the supersonic behavior of the converging diverging nozzle, which is this. So, only for this particular pressure value, this converging diverging duct will act or will work as a fully expanded for full expansion of supersonic stream, full isentropic expansion of supersonic stream. So, when the back pressure is set at that level of pressure 6, we call the nozzle is fully expanded. So, when the pressure, when P b corresponds to level 6, nozzle is fully expanded. And this is the only isentropic solution for supersonic nozzle. There is no change in entropy either within the nozzle or even in the jet downstream. But infinite solution for subsonic case. Infinite number of solutions for subsonic case. This happens because in a supersonic flow the pressure ratio depends solely on the area ratio, while in an subsonic flow that is not so. Let us also consider the mass flow rate. in Lafayette nozzle, say P b by P 0 A T by P 0. At P b by P 0 there is no flow. So, no mass flow, 0 rate of mass flow. Then as P b by P 0 falls, mass flow increases. When P b by P 0 reaches to the level of 0, this is what you see that in this case the choked condition is achieved when the pressure at the throat become the P star sonic pressure, while the back pressure is still less than that. So, P b by P 0, so choked flow condition is achieved before back pressure falls to P star. So, we can call say this is regime 1, and in all these in regime 2, 3, 4 and fully expanded nozzle 4, the mass flow rate remain constant. Similarly, we can also see the how the pressure ratio behaves. In regime 1, in regime 1, pressure at the exit plane remains same as the back pressure, and even at in regime 2, when there is a normal shock within the nozzle, again pressure reaches to exit pressure, Let us say this is the pressure level corresponding to condition 4. After that, exit pressure is not same as back pressure. Initially, the exit pressure is higher than the back pressure, and then again so flow regime 1 and 2, that is where the exit pressure is subsonic and either the entire nozzle is subsonic or part of the diverging part is supersonic. However, at the exit the flow is subsonic and the pressure is same as P by P equal to P b. Beyond in regime 3 and regime 4, the back pressure is again not same. However, again at 6 this will be same. So, this can be taken as level 6. So, this is a typical variation of back pressure and exit pressure relationship, and we will continue further discussion on converging diverging nozzle and its possible use as a supersonic wind tunnel in our next lecture.